So now we're going to do a little reverse engineering. We're going to look at, like I promised, we're going to look at what information is missing from the service manual. And not necessarily missing, but just oversights, things that really aren't necessary from the manufacturer's point of view. They don't need to get into everything. They're not teaching you how to build these radios or even necessarily why they work. You can read through the whole section on circuit descriptions, and even though the things in circuit description are in fact, they are correct by and large, they don't necessarily tell you the interactions between things, like the interactions between ALC and RF amplifier circuits and voltage controlled amplifiers. It's not always very clear. There's a lot of things left out in terms of levels. They don't annotate every single voltage in the radio, and they certainly don't annotate dynamic levels, like actual, conversion gains and how many dB of signal should be present here and there. And there's lots of little things that are kind of left for you to figure out. We're not going to get into all of that. We're just going to look, in this case, we're going to be looking at the bias circuitry on the amplifier board. And to start off, you'll notice I have 3 service manuals here. And since the service manuals are the de facto standard, PDFs rather, are the de facto standard for service manuals today, I like having paper. I like to be able to put post-it notes on a page and making all kinds of little notes to myself of, little things I've changed, or bias voltages, or manufacturing changes that may not be updated. I like paper, but it's not an option. I'm not going to print all this stuff out. But at the very least, it's nice to be able to have multiple board views. It's nice to look at the circuit board. It's nice to look at the schematic and maybe also refer to the service instructions, the step-by-step service literature, tuning procedures, all at the same time, to be able to flip from one to the other. And the only way to do that with the PDF is you have to have multiple copies of the PDF. Obviously, you need space on your hard drive to do that. Delete them when you're done. But for now, we're going to open one. Oh, there we go. We're going to open that one, and I'm going to get rid of this trash on the side of the screen. And I'm going to go back and open another one. If it won't let me open it. No. Got to find out which one's not already open. I want to open 3 of them. And 1, 2, 3. There we go. Okay, so now I have 3 open. 1, 2, 3. And we're going to start. I'm going to go to page, is it 145? And in the next one, we're going to go to page 149, I believe. No, wrong page. Let's see. Well, this one may work too. Unit 1. Unit 1. Okay. And for group 3, not necessarily going to go to the back of the board. I want to go here. So, first thing I'm going to show you is this is the board that we have. We know this by looking at the board visually. And it's the most noticeable difference between this circuit and this circuit is this layout does not have a resistor down here. in this lower right corner. And here you do see that resistor. In actuality, that resistor is missing on the board. So is this device on the board, this transistor. This device feeds from the B plus to the collector of this transistor. And I'm still not quite sure how this transistor was working, even if this was a bipolar device, how this device would have reduced bias as the temperature increased. So it's somewhat unclear. But anyway, it's a moot point because all of this circuitry has been removed. Now, you'll notice up in the right corners here, it says PA unit lot 1 on. And if I go to here, it says PA unit lot 20 on, or lot numbers beginning with serial number 20. And you can go back and forth looking at these schematics, and you will probably not see the difference. And this can be frustrating. If you're trying to look at the physical layout or even look at the schematic and go back and forth between lot 1 and lot 20 and try to see what is the difference between these two devices. Well, the bottom line, and it's tedious, frankly, but if you, for instance, if you look at this part here, let me go back to the board that we actually have. Now, you may be saying, what does this all have to do with fixing this radio? Well, it's important. You want to know the radio. You want to understand what you're doing and why you're doing it. We're going to get to a little bit more specific reverse engineering in a moment. But you take this part right here that's missing. It's R6312. And we want to know, well, what is that part? Or what was that part supposed to be? Or what did it do? Why is it not there? And if you really want to know if a part should be there or shouldn't be there, or if it's, why is it on here? Why are there two schematics? Why is all this information remaining? If this is not what's in the radio, why did they leave it in the service manual? Just to confuse you? Well, yes, and to save money, because it costs money to update all of this documentation. However, following the money, if you want to know what's in the radio, if you really want to know, go to the bill of materials. This is what costs them money. They are not going to order parts and put parts on the production floor or put parts in the machine that inserts things or program the inserter if they don't have to. And that is going to be, this is the bill of materials is Lord and Master on that. The components that make up the board, the components that go into the board, is ruled by the bill of materials. Now here's another thing that's very interesting. If we go down this list, you will frequently see multiple part numbers. You'll say, well, gee, what's the difference between this board and that board? So if we go over here to this column where it says version or lot, here lot, what's the difference between lots? Well, here we have all version 1. And you'll see as soon as you get to a component where it says version 20, version 1, version 11, these are all the same component, but they're slightly different part numbers, but they are the same value. 0.01, 50 mic, boom. You see a better example of that is down here where we have 6315. We have two of them. These are different components. 18K, 27K, slightly different values. Okay, that's not insignificant. Version 30, Same component numbers, both 270 ohms, both 1 watt, different part numbers. They were sourced from a different manufacturer. So it's a slightly different part number. Same component, different part number. And down here we have 18K and 27K for 6315. Different value, almost the same part number. This is RMC 1/10 T. It's the same manufacturer in this value. So this is where you're going to find all the details. This is where the devil lies. It's in the bill of materials. And I always used to look at service manuals and say, God, did they really need all this information? This is like production floor stuff. Well, who really cares about this? Well, it turns out that this can be useful. It's not a reference that you need always, but every once in a while, you got to say, oh, what the hell is this supposed to be? And here's where you can find it out. Now, this is really important because getting back to this is not always right. There are times when you will find a component value on the schematic which does not agree with the bill of materials. And when that happens, the bill of materials rules. Absolutely. Especially if you have a burnt out component, you have a resistor which is just gray and covered with ash, and you have no idea what the color values on that device were. The bill of materials will tell you, even if the schematic is wrong. The schematic's usually right. I mean, it's rare. We're talking, 1% or less of the time that these things are not compliant with what's in the radio. But it's important to know this, that the bill of materials rules. When in doubt, you go by that. Okay, so let's move on. Let's get into this schematic and do a little reverse engineering here. So what we're doing is we are replacing the driver and finals. Here you see the little pre-driver. And we didn't test that, by the way. I'm pretty sure it's okay, but we'll have to get in there and take a quick look at that too, which we will do. Now, this is being driven directly off the supply in J6303, right? Here's our power coming in, J6303. Yep. Okay, so that's our 48 volts. I believe it's 48 supply voltage. And here's our jumper, which feeds our drains. So for the purposes of setting bias voltage and doing testing, we could open this jumper here and be very safe. We wouldn't have to worry about current running away in the drains here and blowing things up and doing a lot of damage. But we've already removed these devices completely, so we'll just leave them like that for the moment. And same thing over here. Here's a jumper. We can open this and remove B plus from the drain so that we can play with our voltage even without removing device. So having these two jumpers available is really convenient. Now let's look at now again, these are voltage devices in terms of the bias is set by a voltage on the gate. And for DC values, the capacitance of the gate and all of that really isn't very relevant. However, the bias voltage, and this is the mistake some people make when setting these things up, the bias voltage is not the set point for the bias of the drain current. It is the drain current, the actual current flowing through the device, which is the bias that needs to be set. So if this requires, say, 100 milliamps of, actually this is probably more like 50, but if this requires, say, 50 milliamps for bias, one device may achieve that at 1 volt here. Another change it out, and another device might not achieve 50 milliamps of drain current until you're up to 1.2 volts here. So it can vary from device to device. So the actual voltage here is not what we're setting. What we're setting is the drain current. This is very, very important. The other thing to understand too, and some people whom I know who have built FET amplifiers like this have set their bias as close as possible to just below threshold, because the instant that they achieve bias current, the instant they actually turn the device on and it becomes active in the AC realm, there would be feedback. There would be positive feedback, either through the supply rails or maybe directly through the circuit or across the grounds, or who knows what the actual path was, but there was either insufficient negative feedback or lack of isolation between drain and gate, or source and gate, and the device would go into self-oscillation and destroy itself. Instant catastrophic failure. So to get the device to work, it was operated just below threshold, where it was actually operating in class B, which is not clean, obviously. Okay, so it needs to be understood that this is a voltage control device, and we are setting the bias here. This is not the bias. This is some voltage on the gate that achieves the bias. So, important distinction. Now, let's look at how do we do this. Well, this one is fairly simple. We have a voltage regulator here. Puts out about 9 volts, if I'm reading that part number correctly. And that voltage is applied through a dropping resistor to a pot, and this is just, there's no, the next resistor to ground here is a 2.2K half watt and a 0 ohm jumper. It's a 0 ohm half watt, as if that matters, but that's the size of the device. It looks like a half watt resistor. Obviously 0 ohms can dissipate any number of watts you like, I guess. So there's our voltage drop across here. This is a little filter, little isolating filter, and a choke, and on through the coupling transformer, and finally that voltage is applied to this gate. Now, the way this is set up, if we want to apply the minimum voltage at this gate, we want to have the maximum resistance in VR. So we're going to remember that. We're going to go back to the board view and see which way to turn all of these pots in order to achieve minimum bias. We want to set everything to minimum and then work our way up from there once we get the meters on these things. That's after we put the devices in. We're going to do this once with the devices out as well. And we should see the same voltage. If these gates are in fact insulated gates, these are MOS FETs, metal oxide silicon insulated gate devices, there will be no current flowing, no DC current flowing in these gates, with or without the devices present. So We should see the same voltages either way. So this is the bias for the driver. And we have our pre-driver back here, and we notice our pre-driver has no adjustable bias. It has instead two diodes to ground. We can look these part numbers up. GMB 01. These are, without a doubt, firmly connected to the heatsink to sense temperature. And we have about 1.4 volts here. And my guess is between 68 ohms and 330 ohms that we're probably looking at, about 0.9 volts here. And that remainder, if this is a 0.7 volt junction, that remainder, that 0.3 volts here, would be reflected across this feedback resistor. And this is a feedback resistor. This 3.3 ohms probably has a pretty fair stabilizing effect on the bias of this fixed bias circuit. And then we have a little bit of actual RF feedback going on between collector and base here to stabilize this from going into self-oscillation. So we have gain control. There's limited gain. This device does not run open loop. And here's an example of where a variability in device gain can be compensated for by having this feedback in there. It flattens it out a little bit, but a large variability in device gain would become a less variable stage gain using feedback. So no adjustments there, but we are going to check this. If these diodes go open, we've got ourselves a problem. Also, interestingly enough, in electronics, we're always taught that forward bias diodes generally run somewhere in the vicinity of 6.8 to 7.1 volts in forward bias. Do a little experiment. Put an ohm meter, or better yet, if you have a digital meter with a diode check. The diode check tells you the actual voltage across the junction. Put your digital meter across a diode, any diode, a 1 in 4000 series, a 1 in 914, whatever you like. Pick a diode. Put your diode check across it, and sure enough, you'll see, 0.68, 0.7, whatever. And take your soldering iron, heat it up. Heat up the diode, and watch that voltage plummet. It'll plummet farther and faster than you'd probably imagine. And hence, there is the temperature compensation circuit for this bias. And it's pretty interesting. I don't know that I've seen a lot of published curves on that either. Occasionally, there are devices specifically designed for that purpose, where of course that curve is published and is very important. But so we'll have to look this device up at a later date. All right, moving on. So this bias is adjustable. There is only one bias for all modes of operation, which means this stage has neither a Class A or a Class AB stage. It's probably AB. I doubt very highly that it's nearer Class A, but we will look into that when we look at the service procedure. Over here now it gets interesting. This is where we get into the Class AB versus A functionality. And you'll notice this switch here in the middle. This is really neat. This is this obviously was deemed necessary because this is actually a fairly expensive thing to do. They have 4 pots where they could have gotten away with 2, and they have a switch. And this switch enables you to turn one device completely off while setting the bias on the other, and vice versa. So you'll see if I push this, well, let's look at it the way it is. It's shown in the operating position where my 9 volts is being supplied to 2 pots. These are 6302, 6304. These 2 pots deliver a voltage to pin 2 here and pin 6 here, which is then delivered through this diode. Here's another dropping resistor, little filter cap, another isolation resistor here, and finally being fed to the gate. This is feedback here with the capacitor in series, so the DC, there's no DC effect here. This is a feedback circuit. We're going to talk about that too. So that's on the other side. We have pretty much the same thing. The resistor delivers to this side through the diode. Same thing to this gate. If we move this switch up, we will now connect pin 0 to pin 4, which means this circuit is open. There is nothing being supplied to this point. It is pulled to ground by this resistor. It is at 0, and it remains at 0, while at the same time this device is now connected to pin, well, that's not pin 7, but whatever this contact here is, which is jumper to 7, is now connected to the bias as it was when it was connected here at pin 6. So this bias is enabled. So we are adjusting the bias on this device. The same thing happens in reverse. If we take the slide switch and move it down, this side goes open and this side is connected, remains connected to its source. Okay, so that's the situation for class A. For class B, AB, we reduce the bias voltage here through this device. This is a switching transistor which reduces the bias voltage at this point by dividing it or reducing it through a 10K pot. Same thing on this side. This device, 10K pot to this point, reduces the bias voltage, which brings us closer to cutoff or VG threshold. And these transistors would be turned on for normal operation in class AB, where the bias current would be significantly lower. So that pretty much is the way the bias circuit's going to read. We're going to put a meter in here. We're going to put an ammeter across these 2 points. We're going to open these connections, put an ammeter in here, and we're going to meter the actual drain current being drawn through these devices in order to adjust the bias. We're just going to check the voltage here just to make sure that everything's working. This is going to be a bit of a pain to do this because we've got to get the whole radio reconnected and plugged in and fired up. But there you go. I could do this with a bench supply, I suppose, but there's a bunch of voltages here. There's 13 volts being supplied for the 9-volt regulator, etc., etc. Okay. What else do we need to go over here? Oh, I know. I wanted to do a little reverse engineering with you on this, on what's going on here in this transformer. And this is one of those instances where the schematic doesn't tell you what's going on. In fact, if I go back to this board view, this transformer here is supplying the main power to the final output. And between this pad here and this pad here, there is a wire. There is a single piece of wire soldered in, a jumper, if you will, which passes through this transformer core. And you don't see it here on the drawing. You do see it on the board, but you don't see it on the drawing. And it may not be important, but it's important to me, and I think it's an interesting thing that it be pointed out. This is the jumper. It's shown as an inductor here. This is the jumper, and it's very interesting that this jumper is not shown as a third winding in this transformer, because that is exactly what it is. This jumper is a third winding in this transformer, and I'll explain now why it's there. This transformer, for those of you who may have had your hands in older solid state, particularly bipolar junction transistor amplifiers of this nature, it is not uncommon to see the supply current is supplied through a center tap on the primary side of the output transformer. So in other words, right where this loop in this primary is shown would be a center tap connected straight up to B+. And that's how current would be supplied to both devices, and how current would be pulled or pushed, as the case may be. It's really pull, but that's how current would be supplied through the primary to generate RF in the output. This transformer is referred to as a virtual center tap. And there's a couple of neat reasons why they do that. One reason is that the bulk of the current flowing through this center tap here flows only through half the winding, and usually there's some capacitance that allows some current to flow through the other side, but that DC current tends to have more of a saturating effect than the RF current. So we want to get the DC current off of this so that the actual dynamic range of the output transformer is increased somewhat. So we get the DC current out of here and into here. These act as a choke. And what's interesting also to note is if I go back to here, you'll see two little dots. These dots denote the phase of the windings. In other words, the ends of these two windings are in phase with each other. And it so happens that this end of this winding feeds this device, and this end of this winding feeds this device. So the power is applied, DC is applied to a phased end and an unphased end. So they tend to counter each other. So this is, I don't know which is phased and which is not here, but either end you could consider either end of these to be in phase with each other. But the current is flowing in opposite directions. Obviously the current from the supply is flowing down in this one, and this current from the supply is flowing up on this side. So they have an opposite effect on each other. So what happens is, let's say this device turns on. This device pulls the voltage down here, which pulls current up through this core. That, since these devices are in phase, the current flowing upwards here wants to induce a current flowing here. And since this is the opposite phase from this side, we're actually going to end up supplying current to this side of the transformer. So half the drain current, maybe actually less than half the drain current, depending on the relative impedance of this versus that. Some of the drain current will flow here, and some of the drain current will flow here. And the same thing happens when this device turns on. Current flowing this way induces a current flowing this way, and by having these two coils closely linked in the same core, we have maintained relative balance in terms of what is, if we call this, well, we can call this current, I1, and we can call the current flowing through here I2, but I1 plus I2 on one device will be relatively balanced relative to I1, I2 on the other device, which is important. That would not necessarily be the case if we simply had a center tap here. If you had two devices with different gain characteristics, it could be a little bit squirrelier than in the case where we have this artificial center tap here with the two separately linked. You notice that these are separately. They're fed separately through two inductors. Interesting change in the design, and I think this was originally a Motorola patent by a fellow by the name of Helge Granberg, who really, if you ever get a hold of an old or look up the Motorola service application manual for RF devices from the 70s, I think every schematic in there has probably got his name on it. Okay, so what about this winding? So this winding, it's one turn. This is, I think, we could take a look when we get back downstairs, but I think about 6 or 8 turns, maybe more, maybe 10 turns, bifilar. And this is one turn. So this is a significantly reduced signal appearing here. It's a relatively small voltage, and in this case it's primarily a voltage source, and it supplies RF to the gate. This is a negative feedback path. This is out of phase with what's going on here. So as this voltage on this drain drops, so too does this. That's negative feedback. For this device to draw current, this voltage has to rise. So as this draws current, this feedback is so configured as to reduce this voltage here. So we have negative feedback. And that has a huge stabilizing effect, both in terms of a gain versus frequency. As we go from low frequency to high frequency, our feedback usually increases in these circuits, although that's not really evident here. I don't see where that roll-off would occur necessarily, but it certainly has a stabilizing effect. And this is very important for when you bias these devices on to prevent catastrophic, prevent them from going into catastrophic self-destruct oscillation. They do have quite a bit of gain. So there's something that is not shown in either the schematic or the layout of the board. Look at the board physically to actually see that. Okay, one more thing to deal with here. Oh, by the way, this diode over here, just so you know, this diode, the purpose of this diode is to reduce the bias voltage, or to drain the bias voltage to 0, to drain these capacitors, or any of the capacitors in this bias circuit after the regulator when this voltage drops to 0. Okay, so it's just that's not a Xeno or a regulator or anything like that. It's just that's just a kill, so it's a clamp, if you will. Clamps the bias voltage when the input bias goes to 0. So it says 13 volts, so it doesn't say it's switched. But I guess they felt that was important, that when you turn the radio off, you kill the bias before the 48 volts drops to 0. Makes sense. Okay. Anything else to cover here? No. So let's go back to, well, let's just take one final look here. To reduce this bias to a minimum voltage, remember, we want to get all these voltages down to 0, or near as close to 0 as we can, for safety's sake, so that when we put these devices back in, they are not capable of drawing current until we start adjusting them to do so. So in this case, we want the maximum resistance here for these two. We want the minimum resistance here for these two, because these pull down through these devices. And we want a maximum resistance here. So in all series feed potentiometers, we want a max, and in these parallel or dividers, we want a minimum. So 3 and 5, the two odd numbers, and 1, 2, and 4 will be a max. Let's go look at our board and come over to the corner, and everything is in one spot. So we have 1, 2, and I suspect that's 5. Why is it not? That's 3. Yeah, I suspect that's 5 because it's fed off the same stripe here. Okay, so maximum resistance for this, we would, if the wiper is in the center, which is this pin here, we want to turn this clockwise. Minimum bias, turning it clockwise. Now that would be counterintuitive, because normally most technicians are accustomed, if you want to turn something up, you turn it clockwise. Not in this case. Over here, it would appear that this pad is open, and this pad is open. So if we want the maximum resistance here, I'm sorry, maximum resistance would be, yes, clockwise. We want to bring the wiper to here, and the other side is connected. Okay, over here we have the opposite condition. We have an open end. So we would want to drive the wiper to the open side. So here we would turn it also clockwise. Here we want to have the minimum amount of resistance. So we want to connect these 2 points directly, the wiper and this pad, to be connected directly. So we would, again, clockwise and fully clockwise would be the minimum resistance across those two devices. Okay, so I think we have enough information to go build on what we were doing. One more thing I just want to discuss. I think this is just a point of interest, not that it's of any use. So if you want to get back to the radio, just skip ahead. But these devices that are no longer there, Q6302, R6312, I don't think we can find R6312, frankly. Well, we can, but we'll take a look at that. But 6312, look at R6308. This is most likely the base of this device. This is a TO202 transistor case. It's in a circuit where very little power would likely be dissipated by this device under any circumstances. Therefore, the size of this device is probably to gain a large thermal conduction area. That they want to use this device as a temperature sense more than a device that actually dissipates power. I'll show you why I say that in a moment. But anyway, R6308 goes from the base to what is most likely the emitter. And the collector is actually fed by 6312. And we'll go look at this part of the board, and you'll see here is R6312, and it's feeding this pad here, which is the center line, which is actually the collector of this device. And if we go to the schematic, you'll see R6308, which was across the base emitter junction, was right here. So base, emitter, and the collector was fed by B plus over here. So R6312 actually if we look here, R6312 is fed here, and then there's a jumper. There's two capacitors, filter capacitors here, and this ends up going over to our B plus 48 volts coming in. So we took the time to figure all that out while you were sleeping. Now, what does that mean? I don't know. I just find it interesting. I look at these things and I just like to know what's going on. The other thing that interests me, which I find a little disturbing, because I think maybe they just cheaped out, or maybe there was some low frequency oscillation, some motorboating problems going on, who knows why. But this device right here, R6316, it's a 10 mic 16 volt cap. It's not huge, but it's an electrolytic. It's fairly large for a bias circuit. Certainly very stabilizing. 1K 10 microfarad. The low frequency cutoff for that combination it's pretty low. I mean, that's a nice stabilizing filter for a bias circuit. But interestingly enough, it's not on the board, and it shows it on the board. It shows the device here. Well, like I said, look at the bill of materials. The devil is in the details, and lacking details, go to the bill of materials, and that's where the money is. Q6316, 10 microfarad, 16 volts, and sure enough, when we go to the bill of materials, where's C? I'm sorry. C, 6316. Oh, there is no 16. It's gone. It's not there. Well, alrighty then. I just wonder why. I just find that interesting that device isn't there. So we have several devices that are not on the board. And obviously, since this is a voltage device. I did it again. Alright, we don't need this anymore. I'm just going to go back up here to the schematic. Obviously, since this driver is a voltage device, there is no need to supply any significant amount of current to it. So I suspect that in the original design of this board, this was a bipolar transistor, which required base current, and probably a fair amount of it. I don't know if it needed a big TO202, but they wanted it to be fed with 48 volts. They put a big dropping resistor ahead of it, and they put a big heat sink under it, and it's without temperature compensation. There does not appear to have been any temperature compensation for that device. A bipolar junction transistor with no temperature compensation and a transistorized device that would more than likely increase the bias as things got hot rather than decrease the bias. It's just all very strange and raises a lot of questions in my brain that'll never be answered. I'll have to go to my grave wondering. There are worse things. Okay, let's get back down to the radio and turn these pots and see if all of our thinking is correct here. And so now we have a good idea of what we're dealing with, what we're doing, how this works, why we do things the way we do, why does the board look the way it does, where are the parts that are missing gone, what are they needed for, what weren't they needed for. And it just adds to our overall body of knowledge. Okay, I really need to apologize here, because I just spent an hour, or better part of an hour, explaining all of this functionality of the power amplifier stage to you, and talking about bias and class A and class AB, and this does that and that does this, and gee, which way do we turn the pots, and so on and so forth. I didn't need to go through all of that, because everything you needed to know was right here. This is it. This is in the circuit description book, part of the book, power amplifier circuit. Hey, who knows better than the manufacturer? The transmit signal from the RF unit arrives at the connector 1 of the PA unit. The transmit signal, 1.8 to 30 megahertz, is delivered to the PA unit and is amplified by pre-driver, driver, and final amplifiers, and exits from the connector 4 en route to the low-pass filter unit. And that's it, folks. That's all you needed to know to service this radio. Simple. Gee, who knew? I'm so sorry. Wasted your time. We're on to the actual procedure for adjusting your driver and final idling current. And there's a few things that need to be changed here, and I think at this point it will make a lot of sense. But starting with our driver idling current here, it says temporarily disconnect the jumper plug between 6301 and 2 and connect the ammeter in place of the jumper. Well, that's in the drain current leg, so that's pretty straightforward. Then it says key the transmitter in either upper or lower sideband with no microphone input and adjust the bias potentiometer for 1.3 amps, and then reinstall the jumper. Well, there's two problems with this, one of which carries on to the final section as well. But the first problem is key the transmitter in either upper or lower sideband. Well, that's fine with no microphone, but we're dealing with extremely low levels of current. We're dealing with that level of current in which the amplifier is doing nothing, is intended to do nothing. It's a very small amount of current relative to the full drive capabilities. And even a very small amount of RF will have a significant effect on the bias. And the problem with that is when the bias is in cutoff, there's the RF is, it's in cutoff. You don't see the RF. And as you bring the bias up, if you bring the bias up to its rated value with a little bit of RF involved, you will be under-biasing the device. And if you actually kill the RF at that point, you'll see the bias level will drop because it's bias plus RF. You have to be absolutely certain that there really, really is no RF driving this final amplifier. And just putting it into putting it into sideband without a microphone is not necessarily sufficient to guarantee that. And I say that for a couple of reasons. One, because if your microphone gain and your audio processor are not all the way down and off, there is very likely just a little bit of noise in the audio section that it could drive the balance modulator to generate a little bit of RF. And it is not uncommon for these analog radios to generate a little bit of RF either in one or the other sideband. It's not always that you get a perfect balance in both sidebands in a balance modulator if they have a shifting carrier oscillator. So therefore, the best way to take care of all of these issues is to simply unplug the drive from the final amplifier and replace it with a dummy load. Put a dummy load on the input and you're pretty much guaranteed that you will have no RF drive. And the dummy load is actually better than a dead short. A dead short, if you do have any instability in the driver stage, that there is any RF or self-oscillation or tendency for generating noise internally, that will be reflected back to the input with a dead short, whereas with a dummy load it will be more likely to be absorbed. So really a dummy load is the way to go, and that's what we're going to do. The other problem I have with this is it does not tell you to turn the bias adjustments to a 0 position before starting this whole procedure, and it really should. If you were just taking a radio that is in working condition and putting it on the bench for the sake of going over it, tuning it up, making sure things haven't drifted over through age and use, then fine. This procedure is probably adequate. However, we're changing finals. We're putting brand new devices in here. We don't know what the gain of these devices are relative to the old devices. It could be higher, could be lower. We don't know if this radio blew up. We don't know if it's unstable. We don't know a lot of things. But we do know that we don't know if anybody went in before us and turned things. We don't know what position these pots might be in from prior hands. So we really want to turn this bias down to 0. And this procedure does not tell you how to do that. It does not instruct you to do that. It doesn't tell you what direction to turn things. So we're going to have to figure that out for ourselves. So those two things are very important. No RF drive, disconnect the drive. No bias, turn the bias down. Let's start from 0 and proceed from there. Moving on to the final idle current. Now that we've gone through how this device works, the starting position is to start with the, see down here, to press the Class A switch. They want to start in Class A, which makes sense because in Class A we are adjusting 1 potentiometer per stage. And then later on we go down and we take it out of Class A and we adjust the other potentiometer for the lower bias of 1 amp. 5 amps is the Class A level, and there we go, and then 1 amp for the Class AB. So that makes sense. And of course there's a switch. Move the switch from the 6303 side to the 6305 side. It goes one final to the other. So we'll go through this again once we have the radio in front of us. So a couple of things to note there, and this could be, quite frankly, this procedure as it's given, it could be a recipe for disaster to the uninitiated, which is why we go through all this. And by the way, just a quick note, I mentioned that if you do key the radio in sideband mode to adjust final bias, you want to be sure that your drive is actually 0, and your modulator balance, your sideband modulator balanced modulator carrier adjustment should be done prior to that. Well, this sideband modulator balance is done 6 pages later after you've adjusted transmitter final bias. 6 pages later. And that's not the way I tune a radio. But that's why I get paid the big bucks. Actually, if anybody wants me to work on their radios, don't contact me, because I probably won't. I really, honestly, truly don't have the time. I don't do this anymore for the general public, which is why I'm doing these videos. I want to share what I've learned over the years with all you folks, so you can do it for yourself, and be satisfied with the job, and not have to be reliant on, other people's golden screwdrivers. But there you go. And we're going to do more of these as time goes on. Wait till I get into phase alignment. Oh boy, that's going to be fun.